Linear functions. That's what today's lesson is all about. Welcome back to another lesson in Algebra 2. In our previous lesson, we looked at transformations of functions. Before that, we just looked at function theory in general. Now it's time for us to get out our microscope and dive in on functions, one set at a time. The first thing I want to look at is linear functions. A linear function, which if you can't guess is what goes in this blank right here. A linear function is a function that can be put in the form of f of x equals mx plus b. So linear functions, I should say of one variable, but that's what we're studying right now, functions of one variable, can always be put in the form of mx plus b. I'm not saying it must be in that form. I'm saying it can be put in that form. The graph of linear function of one variable is in the shape of a line. This is why they're called linear. The slope of a line is the change in the y-coordinate per unit change in the x-coordinate. That's going to be an important part for us, the slope. So with that in mind, I'd like for you to go ahead and practice finding the slope of several different representations of linear functions. Remember, they're the change in the y-coordinate divided by the change in the x-coordinate. So pause the video and good luck. Okay, let's see how we did. Well, in this one here, maybe you remember that the m in mx plus b is the slope. So we could just conclude right away that 3 is the slope. But if you didn't remember that, we would just simply make a table of values. So let's go ahead and take a look at that. Now f of x is our y-coordinate. Y is equal to f of x. And I'm going to put in a 1 for x, and I get 3 times 1 minus 1 is what? 2. Now let's put in a 2 for x. 6 minus 1 is 5. Okay, so what does that tell me? That tells me that as the x increased by 1, the y's increased by 3. And slope is simply the change in the y-coordinates per change in the x-coordinate. And we usually use the letter m, just like in the equation. So the slope is 3. All right, over here we had a table, so I think you were forced to do it that way. Once again, I can find a change of 1 in the x and 4 in the y, and that should be consistent. That's what makes it linear, is that this change is consistent, unless I messed up making the table, which is quite possible. But it doesn't look like I messed up this time. So I'm going to say the slope is 4 divided by 1, which is 4. Okay, so we have an equation here. We can make a table of values, but now that we know that in this form, this number here is the slope, let's solve this for y. So I'm going to subtract 2x from each side. And I'll divide by negative 3. And this time I am going to go ahead and use the distributive property to divide each term by negative 3. I'll divide that term and that term. Remember, when dividing, you have to distribute the division across addition. So a negative 2 divided by a negative 3. 3 doesn't go into 2. So it's just 2 over 3, but the negatives will cancel. Times x. And I can put the x on the 2 or out to the side. I'll just put it out to the side this time. And then a plus divided by a minus is a negative, and I'll 7 divided by 3. 3 doesn't go into 7 evenly, so I'll leave it as 7 over 3. So my slope is 2/3. All right. On this next one, we're looking for the change in the y-coordinate per unit change in the x. If I start right here at what I call a lattice point is where I think it's LITTIC, lattice point is where the graph appears to go through both vertical and horizontal grid lines perfectly. So that one's good. But if I try and just move over one x, you'll notice I don't get a nice even y. So I'm going to try and find another lattice point down here and use a slope triangle. So I went down 2 on the y's per a change of 3 on the x's. You may have heard the term rise over run, right? That's the rise and that's the run. Rise means change in y coordinate, run means change in x coordinate. And slope is rise over run. All right. Do we have any more of those? Yeah, we got a few more. Okay, on this one here, again, we could make a table of values to try and find the slope. I am going to try and put this in y equals mx plus b form, since we discussed that if I can get it put in the y equals mx plus b form, that this is the slope. So I'll distribute the 1/2. 1/2 times x is simply 1/2 x. 1/2 times 8. 8 divided by 2 is 4. And I'll add the 5 over. And so I get the slope is equal to 1/2. And we're going to identify this here as point slope form. And what I want you recognizing is that that number there in point slope form is always the slope. All right, we have another table of values. This time the x is increased by 6, it looks like. And the y is by 8 this time. Let's make sure that's consistent. This time here I added 3, and this time here I added 4. So it looks like a change in 6 in the x resulted in a change of 8 in the y. But when I change the x by only 3, the y changes by 4. So that will reduce. I could say the slope is 8 over 6, but I can reduce that by dividing by 2 on top and bottom to 4 over 3, which is exactly what we got on the other one. So the slope is 4/3. All right, y equals 4. Well, can I put it in mx plus b form? Sure can. It's 0x plus 4. So my slope is 0. What about this one? Ooh, I can't put it in mx plus b form. It has what we think of as being a line shape, but the reason why I can't put it in mx plus b form is because it's not a linear function. Remember, linear functions have to be able to be put into mx plus b form, even if the m is 0. And this graph, when you graph it, is a vertical line through x equals 3, so it would not pass the vertical line test. So this is not a function. And the slope is what we call undefined. And I think looking at a graph of that will make more sense about why that is. So the graph represents all points that have an x-coordinate of 3. So certainly 3 on the x-axis, but also 3, 1 has an x value of 3, 3, 2, 3, 3, etc. So all these points going up, likewise all these points going down. And if I try and find the change in the y over the change in the x, I get a change in y of, really any amount you want. Let's just call it 1. But a change in the x of 0, and we're not allowed to divide by 0. That's undefined. Okay, whereas this line over here, y equals 4, is a horizontal line with a rise of 0 and a run of however much you want, like a run of 1. But 0 divided by 1, that's okay, that's just 0. One other way to remember this, horizontal lines are flat like the top of the Z in 0. Vertical lines are vertical like the side of the letter U in undefined. Okay? So just little bitty tips to remember. And I think we closed off with exactly that kind of situation. So let's take a look at those. So just another example, just like G and H, where we're dealing with vertical lines. We know now that this horizontal line, vertical and horizontal lines, that this horizontal line has a slope of 0. So that's the slope. That is a linear function. It passes the vertical line test. This is not a function. It does not pass the vertical line test. It has a slope that is undefined. So we say a vertical line is a line with an undefined slope. Okay, what I'd like to do is I'd like to derive a formula that would allow us to calculate slope without having to rely on graphing and rise and run and tables. I want to be able to find the slope between any 2 points quickly and easily, so we're going to develop a formula to do that. All right, so I've got a line here. Ignore the units. It looks like this goes through 2. We don't know if it's counting by 2 or 4, and I don't care. I'm trying to get a formula that works in all situations. So if I pick 2 points on the graph and draw a right triangle between them, I can establish a point here which I'm going to use to develop my formula. And this point here must have an x-coordinate of x sub 2 because it's directly beneath that point, and must have a y-coordinate of y sub 1 because it's directly across from that point. I can now develop what must be the run. The run is from from x2 to x1. So I will say x2 minus x1 is the run this way. The rise this way is the change in the y-coordinates, which is y2 minus y1. And since our slope is the change in the y per change in the x, we're going to say our slope is y2 minus y1 over x2 minus x1 for any two given points. So at this point, I'd like you to practice calculating the slope given a variety of different points. So pause the video, calculate the slope, and then we'll go over it. All right, let's see how we did. We know that slope is equal to y2 minus y1 over x2 minus x1. So my y2 in this case, my second y is 6. My first y is 9. My second x is 2. And my first x is 1. 6 minus 9 is a negative 3. 2 minus 1 is 1. And I get negative 3 as an answer. All right, so I want to, before we move over to the next question, I want to ask the question, what would happen if we had changed the order of these points and made them 2, 6 and 1, 9? It would be the same line, right? Any 2 points define a line, so we should get the same slope, but I want to confirm that. Now my y2 is 9, and my y1 is 6. My x2 is 1, and my x1 is 2. Well, 9 minus 6 is a positive 3, and 1 minus 2 is a negative 1. So the negative appears on a different number, but a positive divided by a negative is still a negative 3. So you get the same value as long as you don't mix them up. As long as you establish which point is your x2, y2, and which point is your x1, y1, you'll get the right answer no matter which way you go. All right, let's take a look at the next one. y2 minus y1 over x2 minus x1. Minus a negative becomes plus a positive. 32 minus 20 is 12. 7 plus 3 is 10. And 12 over 10 becomes, let's see here, I can divide each by 2, can't I? 6/5. All right, let's do C and D now. All right, so slope is y2 minus y1 over x2 minus x1, which gives me 30 over a negative 15, which is a negative 2. Slope is y2 minus y1 over x2 minus x1. Minus a negative is plus a positive, so I get 8 over 0. You're not allowed to divide by 0. This must be an undefined slope, and in fact, it is a vertical line. If I were to graph this line, I think it's worthwhile for us to take a look at it. 6, negative 1 would be somewhere over here, but 6, 7 would be on that same x-coordinate of 6, just above it. So that's undefined. And I have a feeling, since I asked you to calculate a slope that was undefined, I have a feeling you probably had to calculate one that was 0. Those are those special cases. We want to build our familiarity with them so that we're not surprised when they happen. Okay, so we have slope of 12 minus 12 over 10 minus 7. Yep, sure enough, and that is a slope of 0. Slopes of 0s and undefined slopes are extremely important. They They occur at very special places in a variety of functions, and they become very important in courses such as pre-calculus, calculus, and beyond. So we definitely want to make sure that we're comfortable with that. Okay, a concept very closely related to slope is what we call rate of change or average rate of change. So let's discuss that. So average rate of change. The difference between average rate of change and slope is that with average rate of change, we can calculate an average rate of change for something that is not necessarily a line. It could be curving, it could be almost a line, it could be all sorts of different things, but we're looking for the average rate in which things are changing. If you listen to the news or you read about different events, you're going to hear about average rates of change constantly. You're going to hear about it in sports when they talk about, the amount of free throws per attempt. You're going to hear all sorts of things happening. How much does this happen per this? Because it's really how we predict future behavior. You know, a player could have scored 100 goals, but if they're 75 years old now, they're probably not going to score anymore. They're not getting their average rate of change has fallen off in recent years. We look at things about average rate of change over a period of time to look and see what's going to happen in the future. So it's really important. But for this lesson, I still want to focus on lines, but we're going to describe it as average rate of change. Okay, I want you to find the average rate of change for this problem, and then I want you to explain its meaning in terms of the problem context, okay? So pause the video and give it a shot. Okay, let's take a look. So we have the average rate of change can be calculated directly from the slope of this line. So I'm going to use a couple lattice points. I'll use this point here. And I'll use 0 because it goes through 0, 0. So it appears as if when I increase from 2 tickets from 0, I go up 150 on the cost in dollars. So I'm going to say if I divide 150 by 2, I get $75 per ticket. And that's the way you find the units. It's always, and if you want to write it like this, that's fine, because we usually put that over here. Yeah, that's better. In fact, that's what I want you to do. We put the dollar sign, when we're looking at rate of change in money, put the dollar sign over what's changing. So rate of change is always, the units of rate of change are always the Y units over the X units, and they're super important. So $75 per ticket. And what does that mean in this situation? It means that's the cost. That's the cost per ticket. All right, let's see what else did we have. The population of Yoknapatawpha County in years since 1900 is modeled by the following linear function. P of t equals 10t plus 2500. Okay, look, got a little shout out to y'all William Faulkner fans out there. You know who you are. Anyway, this linear function here has a slope. We can tell because it's an mx plus b form of 10, right? So if the slope is 10, that's got to be the average rate of change. And what's the units? That's what's so important here. The average rate of change is going to be in people, okay? We're talking about population. That's people per year. So what that means is that the population is increasing by 10 people every year on average. Cool. All right, I think we have one more of these little practice problems to deal with. So let's take a look at this one. All right, we have a change in the time by 1 and a change in the displacement. Displacement is the distance you are from where you started. It's related to distance, right? So plus 1 and plus 30. So I'm going to say that the average rate of change is 30, and we put the y unit over the x unit. Very important. Miles per hour. So that's what you call your velocity. This is the velocity of 30 miles per hour. We can abbreviate MPH. So that's probably a concept you're somewhat familiar with. You may think of it as speed. Technically, velocity can be positive or negative depending if you're going forward or backward. That's really the main difference between the two. All right, so you have an exit ticket. In the world around us, there are many quantities that vary in linear relationships and others that do not. I want you to think of two related quantities that can vary linearly and two others that do not. See if you can come up with some ideas about how the world around you is related between each other. With pieces of the world are related within linear ways, what are related nonlinear. Okay, well, I'll give you one to think about that you can't use. Okay, I'll make it difficult. The population of the Earth is not growing linearly. It is growing much faster than that. And the more people there are on the earth, the more people there are to have children. And the more people that have children, the more those people have children. So it's growing more exponentially. It's growing faster than linear, not at a constant rate. So these kind of concepts are important, how things are related. So think about that and reflect on it, and then I'll see you in our next lesson.